Imagine, for a moment, the age-old dream of rising straight up into the air, not with the gliding wings of a bird or the bounding leap of a grasshopper, but with the effortless, vertical ascent of a leaf caught in a gentle updraft. This vision, the dream of vertical flight, has captivated human imagination for centuries. Its origins lie not in the thunderous roar of jet engines or the sleek sweep of modern wings, but in the delicate spin of a child's toy, in sketches on yellowed parchment, and in the patient tinkering of inventors who dared to challenge gravity in entirely new ways. The story of the helicopter begins not with the first powered aircraft, nor even with the hot air balloon, but with inventions far more humble and ancient. Around 400 before Christ in China, children played with the bamboo dragonfly, a simple yet ingenious toy. With a quick flick between the hands, this little stick with feathered or paper blades would spin rapidly and rise into the air. The toy's secret was vertical lift, generated by the rapid rotation of its blades, a principle so easily grasped by children at play, yet destined to inspire inventors for centuries. As time passed, the fascination with vertical ascent continued to reappear in various forms. In the late 15th century, one of history's most celebrated visionaries, Leonardo da Vinci, turned his attention to the mysteries of flight. In 1489, he sketched what he called the aerial screw, a helical rotor device inspired by his observations of the Archimedes screw and the behavior of fluids. Da Vinci's design featured a linen spiral sail powered by 4 men turning cranks, intended to compress air beneath it and lift off the ground. Though Da Vinci never built his aerial screw, and historians generally agree it would not have flown due to insurmountable weight and power challenges, the concept itself was remarkable. Modern aerodynamic analysis and direct numerical simulations suggest Da Vinci's spiral design could indeed generate lift, albeit inefficiently, and even suppress some of the noise that plagues multi-bladed rotors. The aerial screw became a touchstone for later inventors. Its spiral geometry and bold concept echoed through the centuries, inspiring not only aircraft but also the development of marine propellers. While the machine remained forever earthbound, Da Vinci's sketches marked one of the first moments that vertical flight was seriously contemplated as a matter of engineering, not just fantasy. The centuries that followed brought slow but steady progress. By the 18th and early 19th centuries, inventors in Europe began experimenting with rotary wing models. Launoy and Bienvenu, for example, developed a model with twin rotors fashioned from feathers, and Gustave de Ponton-d'Amécourt, a French inventor, coined the term hélicoptère in 1861 when he built an early steam-powered model helicopter. These machines, while never carrying a human aloft, represented crucial steps toward understanding the mechanics of rotary flight. Yet it was clear that vertical flight posed a set of challenges very different from those facing the designers of fixed-wing airplanes. To lift vertically and hover, a machine must produce enough upward force to overcome its weight, not just momentarily, but with precise control. Whereas a fixed-wing airplane relies on forward motion to generate lift, the helicopter must create lift while often remaining stationary. This requires a rotating wing, or rotor, which slices through the air to create upward thrust. The technical demands are daunting. The rotor must be both strong and light, able to spin at high speeds, and controlled so that the aircraft remains stable and maneuverable. The challenge is compounded by the need to counteract the torque created by the spinning rotor, which would otherwise cause the fuselage to spin in the opposite direction. These problems would stymie inventors for generations. Throughout the 19th century, advances in the understanding of lift and drag, such as those made by Sir George Cayley, laid the groundwork for all forms of flight. Cayley's work was instrumental in clarifying the basic forces at play, but practical solutions for vertical flight remained elusive. In 1843, Cayley experimented with a convertiplane concept, another step in the long chain of rotary wing innovation. Still, the dream remained out of reach. It was not until the dawn of the 20th century that inventors began to close in on the possibility of true vertical flight. The first manned helicopter flights took place in 1907, with the Breguet brothers and Paul Cornu both achieving brief, tethered hops off the ground. Cornu's design, a twin-rotor machine, managed to lift its pilot, marking a milestone in the pursuit of rotary wing flight. Yet these early machines were notoriously unstable and underpowered. They hovered uncertainly, sometimes for only a few seconds, and could not be reliably controlled. Other inventors, such as Jacob Ellehammer, experimented with coaxial rotors, 2 sets of blades spinning in opposite directions to counteract torque. These early 20th century machines, though primitive by modern standards, were essential in demonstrating which ideas worked and which did not. The complexity of helicopter mechanics, balancing lift, stability, and control, meant that their development lagged behind fixed-wing airplanes by about 30 years. Yet the dream persisted. By the mid-1930s, the German engineer Heinrich Fock achieved a breakthrough with the Focke-Wulf W-61, widely considered the first practical helicopter. The Fu-61 accomplished controlled, sustained flight and demonstrated that a rotary-wing aircraft could do what airplanes could not: take off and land vertically, hover, and maneuver in tight spaces. Around the same time, Arthur M. Cecil Way Young was developing the Bell Model 47, another helicopter that would soon become iconic for its reliability and utility. Perhaps the most influential figure in the story of practical helicopters was Igor Sikorsky. Inspired in part by the old dream of Da Vinci's flying screw, Sikorsky built his first helicopter, the H-1, in 1909. It could not fly, but it was a necessary step. His next attempt in 1910 managed to lift itself, though not a pilot. Undeterred, Sikorsky turned to fixed-wing airplanes for a time but never lost sight of the dream. In 1939, he introduced the VS-300, a helicopter that established the now familiar configuration of a single main rotor with a tail rotor to counteract torque. This design proved both practical and scalable, setting the standard for nearly all helicopters that would follow. Despite the triumphs of these pioneers, the fundamental challenges of helicopter flight remained formidable. Helicopters are a type of vertical takeoff and landing aircraft, VTOL as engineers call them, and among all flying machines they are perhaps the most mechanically complex. Their rotors must be precisely engineered and balanced. Control systems must be responsive yet robust. Power-to-weight ratios must be finely tuned, since every extra pound is a burden that must be lifted straight into the sky. And yet, the allure of vertical flight, of being able to rise, hover, and land exactly where you wish, proved irresistible. Today, the helicopter's ability to perform feats no other aircraft can match is taken for granted, but that capability is the result of centuries of dreaming, tinkering, and relentless trial and error. From the spinning bamboo toys of ancient China, to the bold sketches of Da Vinci, to the dogged experiments of Sikorsky and others, each step in this journey was marked by both failure and fascination. The dream of vertical flight, born so long ago, would ultimately reshape what it meant to conquer the skies. Imagine standing beneath the helicopter as its rotors begin to spin, the air thrumming with invisible forces and the machine poised almost weightless above the ground. What makes this possible is a marvel of science and mechanics, a blend of aerodynamic principles and ingenious engineering that allows helicopters to perform feats impossible for most other flying machines. At the heart of this capability are the spinning blades above your head, the relentless whir of the main rotor slicing through the air. Unlike airplanes, which depend on forward movement to generate lift with their fixed wings, helicopters belong to a special class of aircraft known as rotary wing or rotorcraft. Here, the wings themselves rotate, and it is this movement that unlocks the secrets of vertical flight. The main rotor is more than just a set of spinning blades. Each blade is shaped as an airfoil, similar to the wing of an airplane, but designed to operate in a constantly changing environment. As the engine drives the rotor system, the blades cut through the air horizontally, generating lift by creating a pressure difference: lower pressure above the blade, higher pressure below. This pressure differential is the essence of lift, the fundamental force that opposes gravity and allows the helicopter to rise. The faster the rotor spins, the greater this difference becomes, and the more lift is produced. But the story does not end there, because the pilot has a suite of controls to finesse and direct this force with remarkable precision. The two primary controls for managing lift and maneuvering are known as the collective and the cyclic. The collective, usually a lever by the pilot's left hand, is aptly named. It changes the pitch angle of all the main rotor blades simultaneously. By increasing the collective, the angle of attack for each blade is raised, causing the entire rotor system to bite more deeply into the air and generate more lift. This is how a helicopter ascends. Lowering the collective reduces lift, allowing the aircraft to descend. The collective serves as the master control for overall lift, acting on the entire rotor disc at once. But lift alone does not provide control. To move forward, backward, or sideways, the helicopter relies on the cyclic stick, typically found between the pilot's knees. The cyclic is a marvel of mechanical ingenuity. It changes the pitch angle of each rotor blade as it spins, but not all at once. Instead, the angle of attack varies cyclically during each rotation, with the highest pitch and thus the most lift occurring on just one side of the rotor disc. By tilting the disc in the desired direction, the cyclic allows the pilot to direct the helicopter's path. Pushing the stick forward tilts the rotor disc forward, sending the helicopter ahead. Pulling it back causes a rearward motion, and moving the cyclic left or right enables lateral movement. This ability to produce lift variably across the rotor disc grants helicopters their extraordinary agility and unique capacity to maneuver in 3 dimensions. Yet, every action in the air has an equal and opposite reaction, and the spinning of the main rotor introduces a significant challenge. As the engine turns the main rotor blades, it imparts torque to the helicopter's body, which would naturally cause the fuselage to spin in the opposite direction. Left unchecked, this torque reaction would make controlled flight impossible. Enter the tail rotor, mounted vertically at the end of a long tail boom, spinning rapidly to counteract the main rotor's torque. The tail rotor generates horizontal thrust directed against the fuselage's tendency to spin, keeping the helicopter stable and pointed in the proper direction. Roughly 10% of the engine's power is devoted to this task, a testament to its importance. The pitch of the tail rotor blades is adjustable via anti-torque pedals at the pilot's feet. By pressing these pedals, the pilot can increase or decrease the thrust from the tail rotor, allowing precise control over yaw, the nose of the helicopter moving left or right. This not only maintains stability, but also provides essential directional control in flight and during hovering. Hovering itself is one of the great achievements of helicopter design, demanding a careful balance of forces and constant adjustment by the pilot. When a helicopter hovers, the main rotor induces a downward flow of air, generating lift to exactly match the aircraft's weight. But hovering also introduces aerodynamic effects like induced flow and translational lift, as well as the perpetual need to counteract torque. The pilot must continually use the cyclic, collective, and anti-torque pedals in concert, managing the aircraft's position around 3 main axes: roll, which is longitudinal; pitch, which is lateral; and yaw, which is vertical. These axes are not unique to helicopters, but the ability to control them so precisely, especially at 0 forward speed, is what sets rotary wing flight apart. The mechanics that make this possible are a symphony of gears, shafts, and linkages. The helicopter's engine, connected through a transmission, spins the mast and the rotor blades at high speed. The force generated by this spinning is translated into aerodynamic lift through the shape and movement of the blades. Modern helicopter rotors often use advanced composite materials and carefully engineered airfoil designs, some the result of research by NASA and NACA to improve efficiency, safety, and noise reduction. Airfoils like the RC4-10 and RC3-10, for instance, help blades maintain optimal lift characteristics while minimizing drag and vibration. Even with these technological advances, flying a helicopter remains a demanding endeavor. The interplay of forces is constant, and small errors can quickly escalate. Unlike fixed-wing aircraft, helicopters do not require forward motion for their control surfaces to be effective. This means they can take off and land vertically, hover in place, and execute maneuvers in tight spaces, a versatility unmatched in aviation. But it also means pilots must master a complex set of controls and remain vigilant to changes in wind, power, and weight distribution. The pilot's hands and feet are always engaged, adjusting cyclic, collective, and anti-torque pedals to maintain balance and direction. The helicopter's ability to maneuver is not limited to simple up and down or forward and backward movements. By deftly manipulating the cyclic and collective, pilots can execute coordinated turns, sideward slides, and even backward flight. The entire rotor disc becomes a dynamic, tilting surface, allowing for a freedom of movement in 3 dimensions that, for many years, existed only in the imagination of early inventors. Behind all of this lies the science of fluid mechanics. Air, though invisible, behaves as a fluid, and the spinning rotor blades exploit these properties to generate the forces needed for flight. As each blade sweeps through the air, it creates areas of low and high pressure, setting up the lift that holds the helicopter aloft. The ability to control the angle and position of these blades with such finesse is what turns raw aerodynamic force into the controlled artistry of flight. From the meaning of its name derived from the Greek helix for spiral and pteron for wing, the helicopter embodies the marriage of rotation and lift, spiral movement and wing descent. This science and mechanical mastery is what allows a helicopter to defy gravity, to hang motionless in the sky, and to dart in any direction at the pilot's command. It is a testament to human ingenuity, a machine that, for all its complexity, is built upon the elegant simplicity of spinning wings and the air they command. The story of the helicopter's rise from tentative prototype to global powerhouse is one of relentless engineering, wartime urgency, and an ever-expanding vision of what vertical flight could achieve. For decades, inventors experimented with coaxial rotors, explored the mechanics of autorotation, and struggled to coax brief, unstable hops from their machines. Then, on September 14, 1939, a new chapter began in Stratford, Connecticut. Igor Sikorsky's VS-300, with its unmistakable single main rotor and smaller tail rotor, lifted off the ground, not just for a fleeting jump, but for a controlled flight. Sikorsky himself was at the controls. This modest machine, with its tubular frame and exposed mechanics, introduced a configuration that would become the blueprint for helicopters worldwide. Sikorsky's breakthrough did not happen in isolation. Years earlier, in 1936, Heinrich Fock had flown the Fokker-Achilles FA-61, a coaxial rotor helicopter that proved vertical flight could be sustained, maneuvered, and controlled with a degree of reliability. The FA-61's twin rotor system, spinning in opposite directions, solved the troublesome issue of torque without the need for a tail rotor. While coaxial designs would remain a niche, especially outside Russia, they showed early on that helicopter configurations could be as varied as their inventors' imaginations. As the 1930s ended and the world moved toward conflict, the helicopter's promise drew urgent new attention. Sikorsky's VS-300, refined through trial and error, provided the first truly practical platform. Its single main rotor and tail rotor arrangement, perfected through hundreds of test flights, became the dominant design for decades. This period marked a pivotal transition, from the age of experimentation and short, uncertain flights to the era of dependable rotary wing aircraft capable of hovering, maneuvering, and flying meaningful distances. World War II accelerated helicopter development at a remarkable pace. The demands of modern warfare rescue behind enemy lines, rapid troop deployment, and battlefield observation pushed engineers to refine their designs and governments to invest in rotary wing technology. In the years that followed, helicopters began to take on roles unimaginable just a decade before. They delivered supplies to mountain outposts, ferried wounded soldiers from the front, and scouted enemy positions from above. Each new mission drove improvements in speed, reliability, and capacity. The decades after the war saw helicopters branch out into civilian life. The Bell 47, the first commercially certified helicopter, introduced the concept of rotary wing transport to everyday people. Meanwhile, engineers worked to overcome the limitations that had always challenged helicopter design. Early engines, often adapted from automobiles or small airplanes, provided only modest power and kept flight times brief. The introduction of radial engines in the 1920s was a step forward, but it was the arrival of the turboshaft engine in 1951 that truly changed the game. Jet-derived turboshafts delivered more power with less weight, reducing noise and operating costs. Suddenly, helicopters could fly farther, faster, and more reliably than ever before. These engine advances were matched by steady evolution in the materials that made up the helicopter itself. The shift from wood and fabric to lightweight metal alloys allowed for stronger, more aerodynamic airframes. As composite materials entered the scene, engineers crafted rotor blades and structural components that combined strength, flexibility, and reduced weight, further enhancing performance and safety. The overall effect was profound. Helicopters could now be built larger yet lighter, more powerful but also more efficient, robust enough for demanding military missions, and refined enough for civilian air transport. Throughout the mid-20th century, the helicopter's growing versatility became its hallmark. In construction, helicopters emerged as aerial cranes, hoisting heavy components into place in remote or inaccessible areas, a role that fixed-wing aircraft could never fill. In medical emergencies, they whisked patients over traffic-clogged streets to hospitals, saving lives with every minute gained. Specialized helicopters appeared for firefighting, search and rescue, and even as airborne television studios. The ability to hover, land in tight spaces, and lift straight up transformed the helicopter into an indispensable tool across countless industries. Innovation continued at a steady pace. As aviation technology advanced, so did the helicopter. The pursuit of speed, a perennial challenge for rotary wing aircraft, spurred new designs and configurations. Sikorsky's X-2 family, for example, reimagined the coaxial rotor concept, pairing it with a pusher propeller and sophisticated fly-by-wire controls. In 2010, these innovations allowed the X-2 to reach a forward speed of 250 knots, a leap forward in both speed and maneuverability. This design, blending the best of traditional rotors with the efficiency of fixed-wing propulsion, hinted at a future where the speed limitations of helicopters might someday be overcome. Meanwhile, manufacturers like Airbus and Leonardo pushed the boundaries in other directions. The Leonardo AW149, for example, exemplifies the modern military helicopter, modular, multi-role, and interoperable with NATO systems. It can be rapidly reconfigured for transport, medevac, or combat missions, while advanced situational awareness tools help crews operate safely in complex environments. Airbus, for its part, has fielded flying laboratories. Disruptive Lab and Flight Lab to test new technologies aimed at boosting fuel efficiency, reducing drag, and automating flight controls. Their H-160 helicopter, equipped with the Safran Orano engine and distinctive Blue Edge blades, achieves a 15% reduction in fuel consumption and cuts sound by half compared to previous models. Engineers have also embraced digital tools to solve design challenges. Artificial intelligence now helps optimize rotor geometry, acoustics, and energy efficiency, delivering helicopters that are not only quieter and greener, but also safer and easier to maintain. Automation is making its mark in the cockpit as well. Fly-by-wire systems reduce pilot workload, while advanced health monitoring tracks the condition of vital parts in real time, catching problems before they become emergencies. Perhaps most transformative are the emerging trends that point toward the helicopter's next great leap. Hybrid and fully electric propulsion systems are under active development, promising cleaner, more sustainable flight for the decades to come. Civil tilt rotor concepts, aircraft that take off like helicopters and cruise like airplanes, are being explored as a way to blend vertical lift with high-speed travel. Even the venerable tail rotor, long a staple of helicopter design, is being reconsidered, with new approaches that further cut noise and improve safety. Automation and autonomy are opening up possibilities that would have seemed like science fiction to early pioneers. Artificial intelligence-powered systems and advanced sensors can now take over routine flying tasks, freeing up human crews to focus on complex missions. Uncrewed helicopters already serve as scouts, feeding real-time data to operators and acting as the eyes and ears of larger operations. As these systems mature, helicopters may soon fly themselves into disaster zones, hazardous environments, or conflict areas, going where no pilot could safely venture. Today, the helicopter stands as a symbol of adaptability. From the spindly prototypes of the 1930s to the sleek machines filling Airbus's order books, 893 strong in 2024 alone, the evolution of the helicopter is marked by constant reinvention. New rotorcraft concepts unveiled for NATO's next-generation rotorcraft capabilities reflect a focus on modularity and advanced performance, ensuring that rotary wing aircraft will continue to meet the unpredictable demands of tomorrow's missions. The journey from fragile experimental craft to versatile aerial powerhouses has been driven by necessity, ingenuity, and the unceasing quest for new capabilities. Every advance in engine technology, materials science, digital control, and mission automation has expanded what helicopters can do, where they can go, and how they serve society. As new challenges emerge, sustainability, urban mobility, and autonomous flight, the helicopter story remains one of bold experimentation and unbounded potential. The vertical frontier, it seems, is still wide open. In the modern world, the helicopter is no longer a marvel but a mainstay, a tool so deeply woven into daily life and emergency response that its absence is almost unimaginable. Its spinning blades are a familiar sight above city skylines and remote wilderness alike, an audible promise of help, hope, and swift action where conventional vehicles would falter. While the helicopter's journey to this point has been long and complex, its roles today are more varied and vital than ever, with ongoing innovation continually expanding its reach. Nowhere is this more apparent than in emergency medical services. What began as a bold experiment in battlefield medicine during the mid-20th century has become an essential part of healthcare infrastructure across continents. Helicopter emergency medical services, or HEMS, have grown dramatically in recent years. Demand has soared by more than 50% in the past decade, especially in rural areas where distances are vast and road access is unreliable. For many patients in these regions, the wail of a siren on the ground cannot match the urgent thrum of a helicopter overhead. These aircraft routinely reach patients 3 to 5 times faster than ambulances or other ground vehicles, a difference that can mean the margin between life and death. HEMS capabilities have advanced as well. Modern medical helicopters are not just swift transports, they are airborne critical care units, capable of delivering advanced procedures in flight. Highly trained medical crews stabilize trauma victims, administer life-saving interventions, and monitor vital signs, all while speeding through the sky toward the nearest hospital or trauma center. This becomes especially crucial after natural disasters, when roads are washed out or entire communities are cut off from traditional aid. Last year alone, helicopter air ambulance services transported 370,000 patients, providing rapid response and access to regions that might otherwise have been stranded. In these moments, the helicopter becomes more than a machine. It transforms into a lifeline, bridging the physical and logistical gaps that geography, weather, and infrastructure often impose. The impact of HEMS extends beyond immediate trauma care. In disaster relief, helicopters are often among the first to arrive, able to land in areas inaccessible to ground vehicles and deliver supplies, medical personnel, and hope. Whether ferrying in vaccines and food during a pandemic or extracting survivors from rooftops after a flood, their versatility and reach are unmatched. Physician-staffed HEMS have become particularly well established in trauma care, reducing rescue times and increasing the catchment area for hospitals. In mountainous regions, specialized helicopters like the Alouette III and SA-315 Llama have enabled rescues that would once have been impossible, skimming treacherous slopes and plucking stranded climbers from danger. For maritime emergencies, other models, such as the Bell 206B3, Bell 407HP, Bell 4079, and the Airbus AS-350B3 are equipped to handle the unique challenges of offshore rescues and shipboard landings, where timing and precision are everything. Yet the helicopter's role extends far beyond emergencies and rescues. In construction and utility work, it acts as an aerial crane, lifting heavy equipment to mountaintop sites, stringing power lines across canyons, or delivering supplies to remote installations. Firefighting crews rely on helicopters for rapid water drops and surveillance, while law enforcement and search and rescue teams use their agility and hover capability to quickly scour vast areas. The same qualities that make helicopters invaluable in saving lives also empower them to build, protect, and maintain the infrastructure society depends on. In the military sphere, helicopters have undergone their own transformation. Modern designs are rarely single-purpose. Instead, they are engineered or converted for a range of missions, from airlift and medical evacuation to close air support and combat search and rescue. Modular systems now allow rapid reconfiguration, enabling a single airframe to switch roles as battlefield conditions change. Specialized military helicopters perform attack, observation, anti-submarine warfare, and troop transport missions, often in harsh and unpredictable environments that demand both ruggedness and adaptability. The reliability of onboard avionics is paramount, and each new generation undergoes rigorous testing to ensure mission success, whether flying into hostile territory or supporting humanitarian operations. Evolving threats have driven the development of advanced self-protection systems, such as dynamically variable magazines for countermeasures, designed to thwart missiles and other dangers. Attack helicopters, in particular, have become linchpins of modern combined arms operations. They provide close air support to ground forces, take on anti-tank roles, and increasingly operate as part of manned-unmanned teams, a strategy known as MUMT. This approach pairs piloted helicopters with uncrewed systems to share data and divide tasks, laying the groundwork for future multi-domain operations where speed, intelligence, and flexibility will be decisive. Today's military helicopters are more than mere transports or gunships. Advanced avionics, stealth features, sophisticated weapon systems, and robust defensive technologies enable them to conduct everything from high-intensity combat to humanitarian assistance. The premier multi-role utility helicopter, such as the UH-60M Blackhawk, remains in high demand globally, with recent deliveries reflecting its enduring versatility and value to defense forces worldwide. Even as new threats and mission profiles emerge, the helicopter continues to adapt, balancing the requirements of speed, payload, survivability, and ease of maintenance. The world's appetite for rotary-wing aircraft shows no sign of waning. Airbus Helicopters, for example, has recorded a historic backlog and strong orders into 2024, a testament to the enduring importance of these machines across civilian, emergency, and defense sectors. As society's needs evolve, so do the helicopters themselves, with manufacturers and researchers racing to develop the next generation of rotorcraft. The future of helicopter technology is being shaped by a convergence of sustainability, digitalization, and autonomy. Electric and hybrid propulsion systems are moving from laboratory concepts to flight tests, driven by a need to reduce emissions and reliance on fossil fuels. Companies like Airbus are pushing the envelope with experimental platforms such as the Disruptive Lab and Pioneer Lab, exploring hybrid engines, eco-friendly materials, and digital integration. Their goal is to achieve significant reductions in fuel consumption and carbon dioxide output, while simultaneously making helicopters quieter and more efficient. Artificial intelligence is increasingly central to this vision. AI-powered predictive analytics are revolutionizing helicopter maintenance by forecasting component wear and potential failures, leading to improved safety and less downtime. In the design and manufacturing stages, AI-driven tools help optimize rotor shapes for efficiency and reduce noise, while digital simulations model real-world performance long before a prototype ever leaves the ground. The integration of AI into real-time flight analysis, logistics, and even emergency response applications is reducing pilot workload and enabling new mission profiles, including unmanned flights and autonomous deliveries. Looking ahead, autonomous and semi-autonomous systems are poised to transform how helicopters are used in logistics, agriculture, and emergency response. Global Positioning System. Guided flight paths and advanced onboard computers allow helicopters to perform complex tasks with minimal human intervention, freeing up crews to focus on critical decision-making. Uncrewed innovations ranging from drones that scout ahead to data relay platforms that provide real-time situational awareness extend the capabilities of piloted helicopters, making operations safer and more efficient. Design trends are also reshaping the appearance and performance of helicopters. New concepts include single-engine operative modes for fuel savings, unconventional tail rotor arrangements for improved safety and reduced noise, and tilt rotor designs that combine the vertical lift of helicopters with the speed of fixed-wing aircraft. Aircraft like the H-160 civil helicopter incorporate fuel-saving engines and noise-reducing blades, illustrating a broader movement toward quieter, greener, and more community-friendly rotorcraft. Manufacturers are also pursuing modularity and digital integration for the next generation of military rotorcraft. Airbus's concepts for North Atlantic Treaty Organization's future requirements, for example, envision highly adaptable platforms equipped with advanced digital systems, capable of switching roles rapidly to meet evolving operational needs. Sikorsky's X-2 technology and hybrid electric vertical takeoff and landing demonstrators are pushing the boundaries of speed, autonomy, and intelligence, signaling that the pace of innovation is only accelerating. As helicopters continue to evolve, their impact on society grows deeper and more diverse. From the moment a rescue chopper touches down on a remote hillside, to the silent efficiency of autonomous cargo flights, to the thundering support of military rotorcraft in crisis zones, the helicopter story is one of perpetual transformation. Each new mission and breakthrough builds on decades of progress, ensuring that rotary wing aircraft remain not just symbols of adaptability, but active forces in shaping the world's future.